So this is example 3.24, deflection computation by method of virtual forces. So we are given a uniformly loaded cantilever beam shown in the next page. Second, uniformly loaded cantilever beam. Okay. And what are we required to determine? The vertical displacement and rotation at the same point, B. And now you're given that you can take EI as a constant. Now, there are two things to do. Let's first talk about how to determine the vertical displacement, and then we will discuss how to calculate the rotation at B. So for finding vertical displacement, whether you need to find vertical displacement or you need to find rotation, the common step is that you need to evaluate the distribution of the bending moment over the span of the beam for the given loading, the actual loading, whatever loading is given. You need to know their distribution. So the first thing is, this is the given loading, or often we call this as a real loading to distinguish it from those virtual loads. So we often use the term real loading or actual loading for this, or given loading. So for this actual loading, you will apply this actual loading on the beam, same thing as given, and then just you need to determine the distribution of bending moment as a function of x. So these are the reactions, bending, the moment reaction WL square by 2, and this is the vertical reaction. And then you can consider a cut section anywhere, maybe at location x, as you can see maybe on the next slide. No, not given over here, but anyways you can do that on your own, because now I hope you know how to calculate bending moment. So you can consider a cut section over here and write down this equation. Okay, now this equation for M is valid for x ranging between 0 to L. That's fine, because there is no need to, so this moment equation applies to all of the beam, all of the span of the beam. Okay, then vertical deflection, and for finding vertical deflection at B, what you need to do is you will apply a unit vertical force, that's a virtual force. Virtual force is, we call it a virtual force because it is not a part of the actual loading. This is a part of the process for finding deflection at B, vertical deflection at B. So we will apply a vertical force at B equal to 1. And now at this stage, you can apply it either downward or upward, and the final result will not matter. Okay, okay. And so you applied a vertical downward load at B, and then again you need to determine the distribution of bending moment for the beam as a function of x. So delta MVB is just a representation for this bending moment as a function of x is equal to x minus L. This L is a reaction. This moment reaction would be equal to L, because you can say the length of the beam is L, so 1 into L will produce a moment. So you can easily calculate this reaction, moment reaction, and this vertical reaction. Okay, so then this is the formula. I mean, you can cut the section over here at X and draw the free body diagram of either left segment or the right segment, but you need to make sure that X is always defined with respect to the same reference as you did in case of the actual loading. In actual loading, you considered left segment, left side, left end of the beam, fixed one, as the origin for X. So you need to be consistent now. You need to stick to this. You need to take the same origin for this X as well. Okay, so now you have delta MVBX available. Now you can just put these values into your formula. This is what we have discussed in our slides. And now you need to substitute. Now EI is a constant, so 1 over EI can be taken outside the integral, and then just need to substitute mx. This is mx. Okay, this is mx. So mx substituted over here, and then delta mvbx, you can substitute this x minus L. So this is where x minus L, and then you just need to perform the integration. I mean, I shouldn't be explaining how to integrate. Okay, so x minus L squared times x minus L will become x minus L whole cube, and then you can easily integrate this. Minus w by 2, this can also be taken as out as a common, and then you can perform the integration the way you like, and then you will be able to, by applying the boundary conditions, the limits from 0 to L, you will be able to calculate this. Now you would end up a positive sign with this, and that positive sign would mean, this is important, that positive sign would mean that this deflection at B is in the same direction as this unit virtual load. So if you had applied it upward, you would have ended up with a negative sign over here, and that would have meant that you have applied it in the upward direction, and the deflection would be actual deflection would be in the downward direction. So if you have a positive sign, it means this displacement is in the same direction as this applied load, this unit virtual load. And if it is a negative sign, it means it is in the opposite direction. So in this case, it is same positive sign, so it is in the downward direction because we have a downward applied unit virtual load. Now this was the steps to be done for finding displacement at B. Next we need to determine rotation at B. So for that we will apply a unit virtual moment equal to 1 kilonewton meter or 1 kip foot, whatever it is, at B, where we want to find rotation, and then we will determine again the distribution of the bending moment as a function of x. Now this loading will, now you can see that this is just a couple from this side and on this side. So this will be a hogging moment. This negative sign is because it would be a hogging moment. You just stick to what you have learned in the previous lectures. This is the reason I spent a lot of time on our previous lectures, which was regarding bending moment and the sign conventions. Okay, so just stick to those sign conventions and you shouldn't be having any problem doing this. Just need to be able to write how the function of the equation for m as a function of x. Now again, this is valid from 0 to L. Again, we have stick to the same origin for x. We have taken this as origin, the left end as the origin for x in the given beam, in the given loading, actual loading, and we did this in this part, and then we are also sticking to it in the next part. Alright, so then theta b would be equal to, just substitute the values, mx as before, and then theta, this time this is a different value, -1, and then you can easily, you will end up a positive, I'm not sure which sign, let me check. Yes, you will end up a positive sign, and that positive sign would simply mean that the direction for theta b is the same as the direction for this unit moment, unit virtual moment. So this was clockwise, so that's why this is also clockwise. Okay, so you can see it over here. This is the deflected shape, and if you draw a tangent and then you draw a line, you show the angle, it would be clockwise, theta b, and of course VB will be downward.